Good evening, students. So, welcome back to our next session of chapter Permutations and Combinations. So far, we haven't entered into combinations topic, but we are still doing our concept of permutations. So, we just had a brief discussion about the background of these permutations and combinations in our first session. And then in our second session, we just ended up starting with our permutations concept, and we have done questions related to that. So quickly have an overview of what and all the topics in detail that we are going to cover in our today's session of permutations and combinations. So as I mentioned now, so in our previous session, we just started with our permutations, and we have even discussed the important results which are related to the permutations, right? So where we have seen what is NC naught, what is NCN, or else how can we write NCR. So basically, NPR, what is NPN, NPR? So what is actually equal to NPR? NPR is nothing but n factorial by n minus r factorial, which is a brief expansion of our NPR, which we have discussed these conditions in our previous session. And even after that, in the permutations, we basically covered two types. Right, so in the entire permutations, we actually have two types, which is one actually when objects are not alike, that we can say when objects are distinct in another way, and the other is objects are alike. So these are the two conditions where we have in the permutation, and for each of these conditions where objects are distinct and objects are alike, we have seen the conditions. One that is without repetition, right? And the second one is with repetition. So the same case for objects alike also. So what is the formula when we have objects distinct? That is nothing but objects are alike, and that is without repetition. So that is nothing but NPR. Similarly, if it is with repetition, that is n power r. And when objects are alike, then without repetition, what is the formula? So without repetition, it is nothing but NPR divided by whatever the same kind of objects which are alike. So that divided by factorial. That means Q factorial, some S factorial. So like that. So similarly, if we consider when objects are alike and we have considered with repetition, the only difference we can observe is our numerator will be changing. That will be turning out to be n power r, and the denominator will be the same case. Right, so these are the typical cases which we have discussed in our permutations, where objects are distinct, that is nothing but objects are not alike, and the other one is when objects are alike, and the corresponding cases of with repetition and without repetition. Right. So coming back to our today's session, we are just going to continue our permutation part, and we are going to start discussing about the permutation under some restrictions. Right, so far we haven't discussed any permutation condition under restriction. So that we are going to look into our today's case, that is we are going to deal with some cases where permutation under restriction. Right, and after that, so once we are done with our permutation under restriction, so the next will be our combination. So we are going to enter into the next concept, that is combination. The same way how we have discussed for the permutations, like the definition and the corresponding important results and all. So the same will be the case with the combinations also here. So we are going to start this with the basic definition, and after we start with the definition, we'll just deal with some important results which are related to the combination and all. And once we are done with, we'll be seeing the properties. So even in the permutations, we have seen properties. Even in the factorial notation, we have seen the properties. So in the combinations also, we are going to look into the properties in detail. And once we are done with the properties, so the next one will be combinations under restriction. So it's like the flow will be the same thing, like permutation, the properties or the important results, and the permutation under restriction. So the same will be followed for the combination. So we'll be starting with the combination and then properties or some important results of combination and then combination under the restriction. Right. So in our today's session, we'll just continue our next concept of permutation, which is nothing but permutation under restriction. So let's just start with our today's session with this concept, permutation under restriction. So here comes the first one. So we just read out the statement here and we'll be seeing what is the corresponding formula which will be applicable. Right. Sorry. So the number of permutations of n different objects taken are at a time. Right. So here we are taking the permutation for n different objects when taken are at a time. So that is in general. But here in addition to that, we have here one more condition, that is when a particular object is to be always included in each arrangement. Right. So amongst this n different objects, what we have to take? One has to be always included. Right. So how we'll be taking that? So if, for example, if we are having n total objects and R will be the objects which we are be taken, right, to get the number of permutation. But here they have mentioned one particular object will be always included, which means the object which has to be included will be there in n. Right. So what we'll do, as it has to be included, what I'll do is I'll just eliminate that one object. Right. And even I'll eliminate from this R taken, because I know that whatever I'm selecting here R, I'll eliminate one, because one object I have already selected from this n. Right. So let me keep it this way. Let's just have an example. So if for suppose I am having some 5 red balls and some 3 green balls. So total how many n I'll be having? Total 8 balls I'll be having here. Right. Amongst these 8 balls, I have to pick some 6 balls here. Right. So in this, I'll mention that amongst these 6 balls, one should be for sure, it should be a red ball. Right. So I have to take one should be sure it's a red ball. So then what I'll be doing, amongst this 5 plus 3 red plus 3 green balls, I have to sure that one should be red ball. So for that case, what I'll be doing, but I have to select only 6 balls. So from total of 8 balls, I have to take 6 balls in which one red ball should be there for sure in that arrangement. Right. So for that case, what I'll do, I'll just take out first one red ball outside and I'll include that in my arrangement. That means I'll be taking one ball outside that red ball. So my n will become 7 now. Right. So as I have to select 6 balls, but just now I have selected already one red ball. So 1 is already over. So I have to take 5 balls only now. So that will be 7p5. So from remaining 5 balls, I have to select those 5. I have to take those 5 from my 7 balls, because one red ball is already included in my arrangement. Right. So that's why. So 7 is nothing but n minus 1 and 5 is nothing but r minus 1. So for this particular condition, our formula will be nothing but n minus 1 p r minus 1. So now I guess you guys get an idea how we got this formula, that is the number of permutations. So to get the number of ways or permutations of n different objects taken are at a time when a particular object is to be included. So a particular object has to be included in each arrangement. Right. So then it is nothing but the formula, the number of arrangements is nothing but n minus 1p r minus 1. So you can get that idea from this example how we get that. Right. So this is one of the restriction, that is a particular object is to be always included. So that is our restriction here. Right. So let's move on to the next one. So here comes the next one, right? So the next restriction here is the number of permutations of n different objects taken r at a time. So we are taking n different objects taken r at a time. So let's see the restriction here. When a particular object is never taken in each arrangement. So initially we have to include a particular object always in each arrangement, but now the restriction states here a particular object is never taken, right? So we'll just have the same example. So let me take 5 red balls and 3 green balls. So my total n will be 8 balls, amongst which I have to take 6 balls for the arrangement. So the total number of arrangement here will be, and my condition is, so red ball, right? So one particular object is never taken. So one red ball cannot be taken, or else let me include one more thing. So here I will be taking one yellow also. So now my balls will become 9 and I have to select 6 balls. But my condition is that yellow ball cannot be included. That one yellow ball can never be taken in each arrangement. So that is my condition here. So how will we doing that? So amongst these 9 balls, we'll be already having this yellow ball. But here according to the condition that cannot be taken. So now what I'll do, I'll eliminate this yellow ball. So then my number n will become 9 minus 1, that is 8. So I have excluded my yellow ball, right? But should I include in these 6 balls that yellow? It cannot be included, which means excluding this yellow, I have to take 6 balls for the arrangement, right? So in this 8, we already removed that yellow ball. So my number of arrangements will be 8p6. So I have to take arrangement for my 6 balls amongst these 8 balls, which is excluding the yellow ball. So that is their condition. So the particular yellow ball can never taken in each arrangement, right? So this is nothing but 8 is nothing but n minus 1. So n minus 1p r will be the total number of permutations here when the restriction is a particular object is never taken in each arrangement. So from here we can conclude that from these 2 restrictions, if one object is always included in the arrangement, then what will be our formula? N minus 1p r minus 1. And the other is, if a particular object is never taken, then it will be n minus 1p r. So these are the corresponding formulas for the 2 restrictions which we have seen just now, right? So let's move on to the next one. So the next one here is string method. So the next permutation under restriction which we are talking about here is a string method, right? So let's discuss this string method. So the number of permutations of n different objects taken all at a time when m specified all objects always come together, right? So for example, here what we'll say, we are having some okay, let me take a word under. So this is a word. How many ovals we are having here? So this one and this one. So if my question is all my ovals has to be together, that means m specified objects always come together. That means this u and e should be come together. Then what will be my number of permutations? So these are my m objects. So here my m value is 2. Right. So according to the restriction here, see, when we take all at a time, when m specified objects always come together. So I have here mentioned u and e always has to come together, which means my m value according to the statement, it should be 2 here. So now what is the remaining? But my n here is 1, 2, 3, 4 and 5. So my n is 5. Right. So now what are the remaining letters here? N, D and R. Right. So here what we can number? So n minus m plus 1, that is 1, 2, 3 and 4. So this is nothing but 4 factorial into 2 factorial, which is nothing but 2 factorial is nothing but m factorial, and 4 factorial is nothing but n minus m, that is 5 minus 2 will be 3 plus 1 will be 4. Right, so that is nothing but our string method. So string method is always used when we have a statement like when we have to get some objects always come together. So when we have some objects always come together, then we'll be using this method, that is nothing but a string method. So let me explain you again. So let's take this word under, and now I mention the number of permutations of n different objects taken all at a time when all the ovals come together. So for this question, my condition is all the ovals come together. So let's find out what are the ovals, U and E. That means U, E should be always come together, and the remaining will be same, will be different. So N, D and R. So in general, if it is 5, so how many ways these permutations, these letters can be arranged? So N here is 5, that means 5p5, because we have taken all at a time. That is 5 factorial ways. But the condition states here, these ovals always come together. So that's why I'll be keeping whatever come together, I have to make them a box and keep it aside. And the remaining will be arranged like this. Right, so now I'll number. So this together will be always counted as 1 and the others will be single. That is 2, 3, 4. Right, so here we are having 4. The n is 4. So all taken at a time. So how many ways this can be arranged? 4p4. So initially it is 5. But here they have mentioned all the ovals should be come together. So that's why we have kept these ovals in a box. So then our n has been turned out to be 4. So now for these 4, how many permutations we'll be having? That is 4p4. Whereas this U and E can be arranged as UE or EU. That means 2 factorial ways, that is 2p2. So which is nothing but 4 factorial into 2 factorial. Right, so it actually adds to our formula, that is nothing but if we are having m objects always come together. So here m is 2 and n is 5. So if you arrange this formula will be m factorial into n minus m plus 1 factorial. So where n is the total number of different objects and m is the objects that has to be come together always. Right, so this method is called to be string method because we'll be keeping them in a box as a string and then we'll be counting as a numbers. So that's why this will be called as a string method here when we have a condition like always objects has to be come together. Right. So the formula which will be applicable here for string method where the restriction is objects always come together. So here m objects has to be come together, then the formula will be m factorial into n minus m plus 1 factorial. But if we do that box thing and then numbering, that will be the easiest. So that we'll be getting on when we started doing questions. So then it will be easy for us to understand. So let's move on the next one. So the next one we are having is a gap method. So the previous one is a string method and now we are dealing with the gap method. The number of permutations when no two given objects occur together. So initially 2 objects has to be occur together, but now no 2 objects given should be occur together. Right. So in order to find the number of permutations when no 2 given objects occur together, then the formula is given to be m factorial into m plus 1 cn cross n factorial. Right. So if for suppose we'll take the same thing. So here ovals cannot be come together. That means U and E. So in the remaining places, we can arrange the remaining things. Right. So how many places we are having? So our m value here is 2 and n value is 5. So how many places we are having? 3 places. So in these 3 places, what we can do? We can arrange m plus n, that is, we can arrange this n. Right, so the remaining will be 3. Right, so into n factorial. Right, so in this 3 here, it will be n minus m in the formula. Right, so here we'll be arranging. So these two, for these two it will be m factorial, and for these 3 it will be n factorial, because they can be arranged, and in that we'll be selecting amongst this n, we'll be selecting this. So it will be m plus 1 cn. So that will be, you will be understanding when we get into the combination how we'll be selecting that. Right. So amongst this n we'll be selecting 3. So it should be, sorry, it's in reverse. It should be n c m plus n. That is, we'll be selecting 3. So here it should be, here it is n c m plus n. It's a reverse. So this is C. C relates to our combination. So you will be learning what is this combination, what is the expansion of it. So that we'll be learning in front. But now you can see. So for this under, for example, I have given ovals cannot be come together. So I'll just take my ovals and then give the gaps here. So that's why this method is called to be gap. Right. So in these 3 gaps, how many elements can be fixed? So in these 3 gaps, I can fix from this n, I'll be selecting 3. That means 5C3 for these gaps. And those 3, after selecting those 3, I can arrange them in 3 different ways. Because after selecting those 3, here it can be D or else here it can be R. So those can be arranged in 3 factorial ways. And this U and D can be, here E I can have and U, that means they will be arranged in 2 factorial ways, which is nothing but it will be the formula of m factorial into NCm plus 1 into m factorial. So this will be the formula for my gap method. So here it's wrong one. So it's a NCm plus 1. Right. So let's move on. So these are the typical restrictions which we have seen. So first 2 we have seen, and then we have seen our string method as well as the gap method. So now for each of it I have explained you how we get that formula by taking the examples. So now let's get into the question and try and solve them. So find the numbers between 300 and 3000 that can be formed with the digits when no digit is repeated in any number. So this typical question, you guys have an idea how to solve it. So quickly solve it and let me know the answer, because these types of digits question without repetition and all we have already done so far. So quickly do it, guys. And let me know the answer. Quick. So I am not going to explain this. You have to give me the answer, because this typical type of question we have solved, I guess, 2 times in 2 different sessions. So I hope you guys can do it. So you have to check what are the digits given here and what can be placed, because they are asking the numbers between 300 and 3000 only. So the digits between 300 and 3000 will be how many digit numbers? It will be 3-digit number. Three-digit numbers will be having, as well as 4-digit number also. So we have to find the number of arrangements. That means the number of numbers will be in between this 3-digit number as well as 4-digit number, and then we have to add it using these digits alone. So the digits given here are 0, 1, 2, 3, 4 and 5, and no repetition is allowed. So these are the conditions. So quickly solve it, guys. Let's see how many of you could give me the answer. Because there is nothing new in the question. We have already done similar type of question. So read the question, guys. They are only talking about the numbers which are lying between 300 and 3000, and in that only those numbers has to be formed using these given 6 digits alone. That is 0, 1, 2, 3, 4 and 5, and one more condition is added in addition. That is nothing but no repetition of digits is allowed. So here that's why 300 in between they are mentioned. So here 0, 0. So it's in between, right? So 300 is also not counted. Vice versa, 3000 is also not counted. So quickly answer this. So first will be 3-digit numbers here. So here amongst these digits, what are the digits that can take place in the hundreds place? Will it be possible to take 0? No. 1? No, because here they are asking in between 300. So this number will be starting with 3. Right, so hundreds place can have the digits either 3, 4 and 5, which means how many chances we are having here? 3. So that will be 3 into, so one digit amongst these 3 will be always fixed here. Right, so if 1 is fixed, what are the remaining number of digits? So 1, 2, 3, 4, 5, 6. Among 6, 1 is fixed, so the remaining will be 5. So amongst this 5, we will be placing them in these two places. That will be, what are the arrangements? That will be 5p2. So the number of 3-digit numbers using these 5 digits without any repetition is given to be 3 into 5p2. Similarly, you can write for 4-digit number also. So similarly, you can check for the digits which has to be placed in the thousands place, and the remaining will be arranged accordingly. So let's see for the next one. So this is the thousands place. So here we cannot have 0. That's for sure. We can have 1 here and we can have 2 here. But 3 is also not required here because they are asking in between 3000. So for thousands place we are having only 2 possibilities. 1 or 2. So it will be 2 into. So 1 will be already fixed here amongst these two. So the remaining numbers will be arranged in these 3 places. So it will be 5p3. Right. So now the total numbers will be, we have to add these two because they will be not amongst this only one experiment will be formed. They won't be happening simultaneously. So it will be 3 into 5 factorial by 5 minus 3. 2 it will be 3 factorial. So it will be 3 into 5 into 4, which is 60. And here it will be 2 into 5 factorial by 2 factorial, which is 5 factorial. That means 5 into 4 into 3 into 2. So 60 into 2, it will be equal to 120. So the number of 4 digits which are satisfying the condition will be 124 digit number. Similarly, the 3 digit numbers will be 60. So the total numbers which will be formed in between 300 and 3000, which will be satisfying all the given conditions, are nothing but 120 plus 60, which is equal to 180. So this will be the final answer here. Right. So I hope you guys got this one. So let's move on to the next one. So here comes the next one. So read the question. I have explained you the restrictions, how to deal with it. So I hope you can get this one. So give it a try. So they are talking here about even and odd places. So how you will be dealing with that? You have to identify how many number of even places we have, how many number of odd places we have, so that we can arrange those correspondingly. So how many words can be formed from the letters of word article so that vowels occupy the even place. So if vowels occupy the even places, it means the others will be occupying the consonant places. That means the consonants will be occupying the odd places. So first thing will be, we have to identify our number of letters, and then we have to identify the number of vowels and number of consonants, and then we have to identify the even places and odd places so that we could arrange the vowels occupy the even places and the remaining will be the odd places. So let's see how many of you can give me the answer. So it's just a basic application of our restriction. Let's see how many of you has given the answer. So quickly guys, what are the things we have to identify? So this is the word article which is given. So let's identify the vowels first. So A, I, E, and the remaining will be the consonants. That is R, T, C, and L. Right. So these vowels has to occupy even places. So in this article, how many even places will be having? So 1, 2, 3, 4, 5, 6, 7. So total will be 7 places, amongst which we'll be having 3 even places. So these 3 vowels has to be arranged in these 3 even places. That means the number of arrangements will be in 3 places. 3 vowels has to be arranged. That means 3p3. Right. So once we arrange these vowels, we are left with the consonants and the odd places. So how many odd places will be remaining with? 4 odd places. And these consonants has to be arranged in this 4 odd places. That means 4 consonants has to be arranged in 4 odd places. That is 4p4. So the total number of arrangements here will be 3p3 will be 3 factorial. 4p4 will be 4 factorial. Right, so that means 3 factorial into 4 factorial. So let's just expand. So it will be 6 here and 24, which is equal to 24, 14. So the total arrangements of this word so that the vowels can occupy the even places is nothing but equal to 144. So the question can be like this: vowels can occupy the even places. If it is the other way, we can even have it consonants occupy the odd places. So both will be the same thing here. Right. So let's move on to the next question. So here comes the next question, guys. So it's also related to our restriction. So try and answer this. So in this particular question, we have included 3 subsections. So please try and answer this quickly. So read the question. So this is somewhat related to the previous one which we have solved. So read the question, guys. So how many different words can be formed with the letters of the word ordinate? So now the word is ordinate. And first question is, 4 vowels occupy the odd places. So similar to our previous one. So you have to identify the vowels and then even and odd places and then arrange them correspondingly. So in this given word ordinate, how many vowels are there? 4 vowels. So O, I, A and E. So these 4 vowels has to be occupy the odd places. So total number of places here we are having 1, 2, 3, 4, 5, 6, 7, 8. So amongst this 8, 4 will be even places and 4 will be odd places. So in this odd places, these 4 vowels has to be occupied, which means in the other 4 even places, the remaining 4 consonants has to occupy. So give me the answer for the first one. So same method which we have applied for the previous one. So these 4 vowels has to occupy the 4 odd places. That means in these 4 odd places, these 4 has to be arranged. So it will be 4, 4, 4P4 and the remaining 4 consonants has to occupy the 4 even places. So it will be 4P4 arrangement. That means 4 factorial into 4 factorial here. So which will be equal to 4 into 3 into 2 into same 4 into 3 into 2. So that will be equal to 24 into 24, which is equal to 576. Right. So the total number of arrangements so that 4 vowels can occupy the odd places is nothing but equal to 576 ways. Sorry. And the next 2 are pretty simple and pretty direct here. So read the question. So how many different ways we can form so that the word should be beginning with O. So how many places we are having actually? 1, 2, 3, 4, 5, 6, 7 and 8. And amongst these 8 places they have mentioned the word has to be begin with the O. That means we will be fixing this O in the starting place. And here in other place we can have any other alphabets amongst the remaining. Right, so how many remaining we are having? So 7 letters. So those can be arranged in this 7 places. That means 7p7 which is equal to 7 factorial. Right. So similarly, what about the third case? So for our second case, the number of words which will be forming beginning with O is nothing but 7 factorial. So similarly, if the third one, again 8 places. But here beginning with O and ending with E. So in between can take place any other letters amongst the given. So how many letters we are having? 6 letters and 6 places. So it will be 6p6 which is equal to 6 factorial here. So these 2 are as simple as that. So here whatever they have given that has to be fixed and the remaining remaining places can be arranged accordingly in the both questions of B and C. Right, so let's move on to the next. So far we have seen few permutation under restriction and we have done few questions. So now let's deal with some other restrictions. So the number of permutations when two type of objects are to be arranged alternatively. So here when we have two types of objects and we have to arrange them alternatively. So as if they have mentioned, so amongst these two types, let me take one is this and the other is this. If they mention this one group has to be started, so it has to be started with one group, then we'll be starting with one. If they have mentioned it has to be started with group 2, then we'll be starting. If nothing has mentioned, how we'll be arranging these two groups alternatively, right? So the first case here will be, if their numbers differ by 1, put the object whose number is greater in the first, third, fifth places, etc. Right. So if in my group 1, suppose I am having some 10, whereas in my group 11, I am having 11. For example, students. In group 1, I am having 10 students and group 2, I am having 11 students. Then how I will be arranging them so that I could place these group members alternatively. That means group 1, group 2, group 1, group 2. So like that alternatively I have to arrange. So yeah, first thing is I have to observe which group is having greater number. And the difference has to be 1. So here these two differ by 1 and the greater is group 2. So these group 2 members has to be placed first. That means group 2, 1, 2, 1. So likewise we have to start and placing them alternatively, and group 2 will be placed in the odd places. Similar way the other group, that is the group 1, will be placed in the even places. So this is one way of arranging when the two groups are differ by 1. Right. So when the two groups are differ by one objects amongst themselves. So this is the way of arranging them alternatively. So this is our first case. So we'll be having one more case when the two types of objects, that means two groups, the number of students which are present in the groups is same. Right. So group 1 and group 2 here. So in group 1, I am having 5 students. Similarly, group 2 also I am having 5 students. So initially they have differed by 1. But now there is no difference and the total number of students present in the both the groups are same. So now how we will be arranging these two groups alternatively. Right. So for this we actually have two cases. So we have to arrange them alternatively in two cases and both will be considered. So first we'll be taking the first type, that means we'll take group 1, that is 1. So this is my first case, case 1 let me take. I'll start with group 1. So 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. So this is how I'll be arranging my members accordingly, starting with my group 1. And the other one will be case 2. Here, initially I have started with my group 1. So now I will be starting with my group 2. That means here it will be 2, 1, 2, 1, 2, 1, 2, 1, 2, 1. And for this, we will be having the arrangement. And this case also we will be having the arrangements. To get the total arrangement so that we could arrange these two groups alternatively, we have to add this case 1 arrangements and case 2 arrangements. So that will be giving our total number of arrangements when we have two groups with same objects. So that's how we'll be arranging them alternatively. Right. So this is one more restriction where we'll be arranging objects in them alternatively. Right. So let's go ahead and do some questions related to that. So here comes the question. So read it and try to understand and do it. So quickly guys. So I have explained you in detail how we will be starting and solving this alternative things and all, because here I have considered groups. You can take group 1 students and group 2 students, and how we'll be arranging when these two groups have same number, and how we'll be arranging when they'll be differing by one object. So get back to the question. So read it. So here the case is same. That means our second case. First read the question and try and understand it and then answer. In this also we are having 3 subsections. That means 3 questions here. Quickly read the question, guys. I'm just looking for the answers if anyone could give me. And if you have any doubts also, you can just question me in the comment section. You can do that.
Yeah,
So we'll just read out the question. So find the number of ways in which 5 boys and 5 girls can be seated in a row. So here we are having 2 groups. One group is having 5 boys and the other group is having 5 girls here. Right. And amongst this, the first question is no 2 girls may sit together, which means here we have to arrange them alternatively. That means no girls, so that no girl may sit together. So the first one is no 2 girls may sit together. That means alternatively. So first case what we can do, we are having 5 boys. So let me take B1, B2, B3, B4 and B5. Similarly, we are having 5 girls, G1, G2, G3 and G4 and G5. Right. So no girls may sit together. So let's arrange boys first. So B1, B2, B3, B4 and B5. So if we could arrange these boys first and in the remaining places we could arrange the girls. So boys will be arranged in, so here I have given B1, B2, B3, B4, B5, but they can be rearranged. That means boys can be arranged in 5P5. That means here how many are there? 5 boys and 5 places. So 5P5. And what are the gaps where we can fill up with the girls? So here 1, 2, 3, 4, 5 and 6. So we are having 6 gaps amongst which we have to arrange the 5 girls. Which means this alternative arrangement can start with girl or else it can start with boy 1. Right? That is 5p5 is equal to 5 factorial into 6p5, that is 6 factorial by 6 minus 1, that is 1 factorial here. So here the total number of arrangements so that no two girls may sit together is given by 5 factorial into 6 factorial. So these are the total arrangement, that is total number of ways so that no two girls may sit together. Right, so it's as simple as that. So they have mentioned no two girls may sit together. So we have arranged first boys, and then in the between places, in the gaps between them, we have arranged the girls, which results to be 5 factorial into 6 factorial. So let's move on to the second question in this. All the girls sit together and all the boys sit together. So here we are having 5 girls, that is G1, G2, G3, G4 and G5. So they have to be sit together. So just now we have seen whenever they have to be together, we'll take all of them and keep them in a box. Similarly, boys also be sit together. So B2, B3, B4 and B5. So these also to be placed together. So how many ways we are having? 1 and 2. That means these two will be arranged in 2 factorial ways. And inside 5 girls, they can also be rearranged and placed. That means 5 girls are there, they will be arranged in 5 factorial ways. Similarly here 5 boys are there, they can be arranged in 5 factorial ways. So the total number of ways which we can arrange so that all the girls sit together as well as all the boys sit together is given to be 2 into 5 factorial square. Right. So let's get back to the next one. That is our third question here. So third one is find the number of ways when all the girls are never together. So whenever we are having this never together concept, so before getting into directly never together, we'll just we can go by all together. So first what we can do, we'll just take what happens, what is the number of arrangements when we take all the girls together. Right. So that means I'll be taking all the girls together first. And remaining boys can be placed. So B1, B2, B3, B4 and B5. So let's start giving numbers. So this box, entire box will be given with 1 and 2 here, 3, 4, 5 and 6. That means 6 factorial into these can be arranged inside, that is 5 factorial. So 6 factorial into 5 factorial. So this is the total number of ways of arrangement when all the girls are together. But the question here is are never together. So we'll be subtracting this from total arrangement. So total arrangement is nothing but how many number of boys and girls we are having. So 5 plus 5, 10. So total arrangement will be 10 factorial. So for never together, we'll be separating this all together from the total arrangement. That means 10 factorial minus 6 factorial into 5 factorial. So this will be the total number of ways where all the girls are never together. Right. So this is how we'll be solving whenever we are having a groups of equal objects and the questions given accordingly. Right. So that's all for today. So in our today's session, we just finished our permutation under restriction. So in our next session, we'll just start with our next topics and continue our chapter of permutations and combinations. So if you guys have any question, any query in this chapter or session, you can let me know in the comment section.